Hello everyone, my name is Rob Holes and I'm the Vice President of Hydraulic Controls Incorporated. Today I'm going to discuss some of the advantages of variable speed fan drive cooling systems and then go into more detail regarding brushless electric fan technology. At the very end of the presentation, I will show you a SPAL brushless fan in action by giving you a short demo. So before we dive right into brushless fan technology, what are variable speed fan drives and why should we use them? And a good way to understand this is by comparing variable speed fan drive to a direct drive fan. Now, direct drive fans are coupled directly to the crankshaft of the engine, and they're designed for continuous peak power in extreme environments. So what does that mean? That means under full load and in its most extreme operating condition, which could be Arizona in the middle of summertime. Now, how often is that machine going to be under full load and in those extreme environments? Not very often. In fact, less than 5% of its operating life are even going to be close to those extreme environments. So that is horsepower that you're losing by spinning that fan all the time at engine speed. Now for variable speed fan drive systems, what we do is we measure the temperature of whatever we're cooling, then we'll set the minimum value, the minimum temperature, which will be 0% fan speed, and then we'll set the maximum temperature, which will be 100% fan speed. And the power savings is going to be achieved by varying the speed of the fans based on that real-time temperature demand. So in this example, I set the minimum setting for 160 degrees Fahrenheit, which would be 0%. I set the maximum setting for 220 degrees Fahrenheit, which is 100%. And you can see as I ramp up the temperature, the demand, you can see that the fan is slowly going to ramp up until I reach 100% fan speed. Now remember in the previous discussion that 100% fan speed would be for maximum load and maximum environmental conditions. So most of the fan's life is going to be spent around 20 or 30% fan speed. There are several applications out there where variable speed hydraulic fan drives are very beneficial. That is why I wanted to show this slide, which compares direct drive fans to variable speed hydraulic fan drives. Some of the key characteristics for direct drive are its inefficiencies, its noisy operation due to the fact that the fan is directly coupled to the engine, and its fixed mounting location right in front of the engine. Now with a variable speed hydraulic fan drive system, you can relocate that fan, right, due to space constraints. Also, you're only running the fan at the speed it's demanded. So it might only be running at 20 or 30%. So it's going to be much quieter and it's going to be much more efficient. Now let's look at some key reasons for choosing variable speed electric fan drives over hydraulic. The key negative takeaways for hydraulic fan drives is that they take a lot of space, they're very labor intensive, they have high maintenance requirements, and one fan is used to cool all cooling systems, which means the fan will run at whichever cooling system has the highest demand. We'll touch base on that a little bit later. Also, this system can only be tested after being fully installed. Variable speed fan drives have several advantages, which includes they take up less space and are easier to relocate. They only have electrical connections, so they're very easy to test. They're very low maintenance, and separate cooling systems can be cooled based on individual demand. Now that we've established that variable speed fan drives are beneficial, let's look at a few design criteria for hydraulic versus electric. Variable speed hydraulic fan drives are still very efficient compared to direct drives. They are also great for moving large amounts of air in high pressure applications, such as thick heat exchangers or stacked cooling packages. Now, variable speed E-fans are easy to relocate, but are only good up to a certain amount of pressure, so they wouldn't be able to accommodate a heat exchanger, say 10 inches thick. But one feature that makes E-fans more efficient is that they can cool individual cores separately based on their individual demands. For example, with a multi-core heat exchanger, you can you can be cooling the charged air at 10% fan speed, the transmission cooler at 30% fan speed, and the engine cooler at 60% fan speed. Let's review some of the key benefits of brushless E-fans. Fuel efficiency up to 15%. I've done studies where we achieved up to 10% fuel efficiency with variable speed hydraulic fans. Now with E-fans, you generally gain about another 5%. Increased horsepower. That is horsepower that can be used elsewhere on your machine, critical for Tier 4 applications. Significant longer life over brush technology. Brushed fans typically last about 5,000 to 6,000 hours. Brushless fans will last about 30,000 to 40,000 hours at full speed, but you almost never run these fans at full speed. We talked about ease to relocate already, decrease space constraints, reduce weight, reduction in noise levels. These fans are only running at a percentage of their maximum speed. Reduction of debris on the radiator screen and less dirt in the engine compartment. I'll give you some examples of this later on in the presentation. Low EMI, electromagnetic interference. Very important as you add more electronics to your machines. And these fans are great for adding to existing applications as additional cooling in extreme conditions. So now let's talk about the advantages of brushless over brush technology. So why is brushless technology so popular? Well, when you go into purchase power tools these days, almost all main manufacturers have gone to brushless technology. And there's a reason for that. The absence of brushes eliminates the problem with overheating and breakdown. You also do not have friction between the rotor and stator, which reduces wear and maintenance, resulting in, of course, longer life. The reduced friction also eliminates sparking due to intensive loads. Brushless technology is also about 10 to 15% more efficient. But let's talk about some of the cons. Generally, brushless products typically cost more, and that's mainly because of the onboard electronics. Also, when it comes to fans, you'll generally need a controller with some type of external controller. Now I want to talk specifically about the features of SPAL brushless fans. SPAL offers a variety of brushless fan products, pushers, pullers, anywhere from 10-inch fans all the way up to 18-inch fans. All these fans are variable speed outputs. They generally exceed 30,000 hours, even though I've seen some fans that are rated for 40,000 hours, and that's at full speed, which these fans are hardly ever run at full speed. They typically have a 3-year warranty. Very high efficiency, high performance fans. And one key feature too, especially for mobile applications or harsh environments, is the fact that these motors are sealed. They're dust tight, and you can also pressure wash these fans. These fans are made for 12 and 24 volt DC operation. And some of these fans come with reversing capability. So if you wanted to throw it in reverse for X amount of time to blow out debris from the radiator, these fans have that capability, or some of them do. These fans have onboard electronics, self-protected. They go through vigorous environmental testing. And they have reduced NVH or noise vibration harshness levels. So part of the brushless technology is the fact that there's no sparking, which I've sold these fans into applications that go underground mining or even military applications. Now also for mobile harsh environment applications, very important is the slinger hub. So the slinger hub actually attaches all the blades together on the outside. So if something accidentally hits one of the blades, generally it's not going to bend that blade and then have to throw away the fan. It's actually going to make it more rugged so it can actually handle those harsh environments. Hello everyone. For this video clip, I just wanted to give you some examples of a few different SPAL fans, some characteristics of those fans, and some different ways to mount these fans. So first let's start off by just looking at this 10-inch variable speed SPAL fan. 12 volt, 4100 RPM, produces about 1300 CFM. This fan is a polar fan, which means it sucks air this direction and pushes it out this direction. Very traditional. Also on the back here, we can take a look. We have the onboard electronics, and then we also have the different colored wires here. Now the yellow and the white wire are control wires. The white wire is PWM wire, and the yellow is the analog input wire. You can use either one. Then you also have the red and black wires, which are just power and ground. Also, one thing to note, and we talked about this earlier, is the slinger blade. Very important for harsh environments. I've used a lot of brush fans through the years. A lot of them hit something small and bend one of these fan blades, and it's done. So attaching it all together with the slinger blade, very important for harsh environments. So next, let's take a look at this 12-inch fan. So this is a high power motor one. So it's a 4100 RPM fan, and at max it has 12 volts. So maximum speed, you're looking at 40, probably amp draw is going to be between 40 and 45 amps. But it's also going to produce up to 2200 CFM. So a lot more airflow. This is a pusher fan, sorry, it's a pusher fan. So air will go this direction and out this direction. So if you really like this fan, it meets all your requirements, and there's no other fan, and you need a puller fan, what you can do is you can simply build a shroud, and you're able to mount it in this direction. So then it will pull air through this way and out this way. And I'll show you an example of that behind me. Also, one thing to note too is this fan only has one input wire, PWM. So, and the reason for that is this fan also has the capabilities of going in reverse. So, if you're running normally throughout the day and everything's working fine, but all of a sudden you see a little bit of debris or something in front of the heat exchanger and you want to blow air backwards, you can simply throw this thing into reverse and it will spin backwards for whatever time you program that for. Let's take a look at a couple different mounting options. Now we talked about the 12-inch fan, how you can mount it in either direction. Well, here we have one bidder that has a hydraulic oil cooler, and what they've done is they use a 16-inch variable speed SPAL fan, and this particular fan is a pusher fan, but they needed it as a puller. So what they did was they just mounted it in the opposite direction, and you can see the shroud is a little bit thicker, because most of the fan is actually inside the shroud. Over here we have a much more traditional setup where we have a puller fan. The shroud's a lot thinner, but most of the fan is externally and it's pulling the air through. So just a couple of different ways that you can mount these fans. Now let's take a look at a couple of different control methods. There's a lot of different control methods. These are pretty typical. Just a couple of easy ways to get these fans up and running. So here we have an EMC controller. So this controller can tie into your CAN bus, can tie into sensor inputs, 0 to 5 volt, the thermistors, which I'll show you in a minute. Has a USB port, a mini USB port that you can easily plug in and program it, configure it. You don't need to be a programmer to configure this thing. So just an easy controller to get set up. This is a single bank controller, and what that means is that it can run one fan or it can run 10 fans, but they're all going to be going at the same speed. So let's say you had an array of 4 fans hooked up to this controller. You can easily run them at vary the speeds, but all the speeds on the fans will be the same. Very powerful, encapsulated for harsh environments. This particular controller is through SPAL. It's preset at the factory for different temperatures. So there's like 4 different varieties of these sensors. They simply screw into the side of your heat exchanger and power and ground and plug into the fan, and it will control the fan through a PWM signal that is created in the circuitry inside of this. Very inexpensive way to go, not very complex. but can get you up and running for simple applications. There are a couple different sensors just to take a look at. These are really common. They're very rugged. They can last in harsh environments. This is an air sensor. It can be used for charge air. It can be used for compartment cooling. Anywhere you're just measuring air temperature. This is a wet sensor, engine cooling, hydraulic oil, anything that you need to use for that. They can plug right into the EMC controllers. They can plug into your system controllers as well. So just some very inexpensive ways to check the temperatures on your heat exchangers. Well, thank you for joining me, and I hope you enjoy the rest of the presentation. There are a couple of different ways to control a SPAL brushless fan. Some fans have an analog and PWM input, and others only have a PWM input. The most common method of control is by using the PWM input and adjusting the duty cycle to control the speed of the fan. In the fan datasheet, you will find a graph similar to the one on the right, and also a frequency range to use. 100 Hz can be used for the majority of fans in the catalog. Next, set the minimum and maximum duty cycle to run the fan from minimum to maximum speed. In this case, by looking at the chart, the minimum speed would be 25% duty cycle, and the maximum speed would be 90% duty cycle. As I ramp the duty cycle from 25 to 90, the fan will linearly progress from the fan's minimum speed to its maximum speed. Also note that the SPAL fan's minimum speed varies. Most of the time, the minimum speed will be 25 to 35% of the maximum speed. In order to turn the fan completely off, 2% duty cycle is used. This fan also has a reversing feature. At 12% duty cycle, the fan will ramp to full reverse. When using the analog input, you will need to attach the PWM input to ground. Then you'll be able to use the analog input to control the fan. From the chart on the right, we can see that we can run our fan from minimum speed to maximum speed by ramping the input from 2 volts DC to 10 volts DC. I've also had a few applications where customers simply want to control the fan on and off. In order to do this, connect the PWM input to ground and switch the analog input to plus power. This will cause the fan to ramp up to 100% fan speed. To recap, some of the key features of brushless fans are: they are variable speed, the power used is based solely on the cooling requirements or demand, the fans are completely decoupled from the engine RPM and take advantage of less work required. But my main point of this slide is to help you understand the current draw of a typical SPAL brushless fan. The graph on the right shows the fan speed as a linear function from minimum to maximum. As you can see, the current draw is not linear. For this application, you can see at maximum speed, 4,800 RPM, my current draw is about 40 amps. If I decrease my fan speed in half, my current draw is about 5 amps. You can see the benefit, since most machines' operational duty cycle will require less than 60% fan speed. There are several different ways to control these SPAL brushless fans. Over on the left, upper left, I show some configurable controllers by Innovation Controls. These are designed specifically to drive SPAL brushless fans, and they can tie into the CAN bus or any type of analog input or thermistor. The EMC controller is a single fan bank controller. It can control multiple fans too, but they all run at the same speed. The EMC6 controller can control up to 6 different banks of fans, running them at all different speeds. It also has an output that can be configured as a variable speed hydraulic fan drive. Below that, I show some SPAL controllers that are very simple, but they're preset at the factory for temperature ranges, and they have onboard electronics that just produce a PWM signal and tie right into the fan. Over on the right are some different ways that you can use your existing system controller that's on your machine, whether it be Bosch, Innovation Controls, Hydroforce, Hydac, whichever system controller that you use, and you can simply output a duty cycle, PWM signal and control the fans directly with your controllers. Below that, I show an array of different sensors, thermistors that can be used for wet, dry, or even pressure transducers that can be used maybe for AC applications. I just want to give you a quick overview of the EMC controller. This controller was designed specifically for driving SPAL brushless fans. Has several different inputs, several different outputs, but one nice feature about this, it has a graphical user interface, completely configurable, downloadable from Innovation Control's website for free. You can easily go through, set up all your parameters, and control the fans. So here we have a very simple fan controller made by SPAL. This controller is basically a thermistor with onboard electronics that produces a PWM signal to your fan, and you'll also have a power and ground input. This controller also has an input for an override, so you can connect a switch up to it and turn the fans on full speed if you want to. The temperature ranges for this controller are set, so there's 4 different varieties with 4 different part numbers. So let's talk about applications. Over on the left side, I have a whole list of different applications that I've been involved with that utilize SPAL brushless fans: engine cooling, transmission, charger, hydraulic oil, engine compartment, air conditioning. I mean, the list goes on. You can see, and the list just keeps going on and on. Now, as far as application examples, I just listed the main ones here, but there's so many out there. Hydraulic oil cooling, huge market there. Electronic component cooling for servers, compartment cooling, diesel exhaust, for example, is just one compartment, could be an engine compartment. Electric and hybrid vehicles where power efficiency is a must. Industrial applications, air circulation, machine cooling, reducing emissions, tier 4 applications where you need to get that horsepower to where you need it. And also, I've run into applications for food handling, fruit drying, which actually uses the fans to actually dry off the fruits on the conveyor belts. So, it's really whatever you can think of that could utilize this type of technology. Now here's a great application that really highlights the benefits of brushless fan technology. This is a tree shaker that was completely redesigned to meet Tier 4 requirements. This meant the complete redesign of the chassis and the hydraulic system to be fully operational with a smaller 74 horsepower Tier 4 engine. The smaller Tier 4 engine was about a $15,000 savings over the larger engine, which would trickle down to the customer as a lower purchasing price. So after the machine was built and in the final stages of testing, the customer noticed that the machine worked great until it had to shake very large mature trees. Set to full power, the machine simply would die. They needed just a little bit more horsepower to run the hydraulic system. Hydraulic controls worked with the customer. We actually swapped out the direct drive with 3 SPAL brushless electric fans and an EMC controller in under 3 days, just in time for a scheduled live demo. The machine worked great, even on large mature trees. Here's a video of a tree shaker in action. Notice the amount of debris that falls on the machine every time it shakes a tree. Remember, the main reason for installing the brushless fans was to gain horsepower, which we did, but there were many other key advantages that included increased fuel savings, reduction in fan noise, very noticeable. As we were testing this machine out in the field, they almost thought there was something wrong with the machine because they were used to hearing that loud noise coming from the direct drive fan, and they just did not hear it because the fan was only running at 20 to 30% most of the time. Huge reduction in debris in front of the radiator screen. For this industry, that's a major cause of overheating. And then also less dirt and debris being sucked into the engine compartment, when we got back after a full day of testing in that nasty environment, they usually like to open up the engine compartment and wash it out. But in this case, they opened it up and there was no dirt and debris in there. Again, because the fans are not running at full speed, sucking all that dirt into the engine compartment throughout the day. After having success using brushless fans, we started to look at other applications that could benefit the machine. One way was to relocate the air conditioning condenser. This had several advantages. This allowed more airflow to the radiator. We also can go with a smaller, higher fin count condenser since we won't be sucking outside dust and debris through it. And we maximize compressor efficiency by measuring the system pressure with a pressure transducer and regulating airflow to maintain optimal system pressure. Brushless fan drives have been around for several years now and are making their way into several different applications. Here are just a few examples. Almost all major manufacturers of excavators have gone to brushless technology, mainly for packaging requirements, fuel economy, and increased available engine power. We discussed earlier about the advantages during the machine design stages to relocate these cooling systems. Here are two perfect examples of this. On the upper left, this is Vermeer's new directional drilling machine, along with, in the lower right, the latest in Tier 4 rough mower technology. Here are a few more examples, including a few gensets, some portable generators, and a telescopic boom lift. Now that we all have a good understanding of brushless fan technology, I'd like to just take you through a brief demo. Okay, before we get the demo started, let's go ahead and look at the demo setup. So here we have a 15.2-inch SPAL, variable speed brushless SPAL fan connected up to this heat exchanger, which is for hydraulic oil, so we'll be driving this. And we're going to be using this demo kit provided by Innovation Controls to simulate the temperature inputs. So on this demo kit, what we have is we have an EMC and we have a controller and an EMC6 controller. The EMC controller is a single bank output, meaning it can drive multiple fans, but all the fans are being driven at the same speed. So it can look at multiple temperatures and determine exactly which one has the highest demand, and that's how fast the fan will run. The EMC6 controller is unique that it has 6 output banks that it can control. So you might have transmission charger, hydraulic oil cooler. You can run all those banks at different speeds, which is really the most efficient way of cooling. The EMC6 controller also has a variable speed hydraulic fan drive output as well with reversing capability. So just to note that if you're running a thick heat exchanger that needs a hydraulic fan drive, variable speed, you can run that, and then you can break off things like your charger, your transmission, your hydraulic oil coolers, and run that with the other output banks as well. Up here we have a display. The display is actually simulating the ECU. So we can monitor, we can actually change the engine temperature, we can change the charger, intercooler temperature as well. We can change the engine RPM. So these are things we can adjust up here. It sends those signals J1939 down to the EMC controller, and we can make a decision on how fast to run the fan. We're also looking at a potentiometer that's down here on the bottom of the demo kit that we can adjust. It's a temperature input, but that goes to the EMC controller. EMC converts that to J1939 and sends it up to the display, so we can actually monitor that as well. It's also sending fan RPM, converting that, sending that information, J1939, up to the display as well, so we'll be monitoring that. We also went ahead and hooked up a current meter. So very important to look at the current draw on some of these fans. It's very interesting because it's not linear. So as you back off the fan speed, the current drops very quickly. And it's interesting to monitor that. So that's why we have this connected up here as well. So let's go ahead and get this demo started. Okay, so with this demo, what we're going to do is we're going to drive a brushless SPAL fan with it using an EMC controller. And we're looking at 4 different inputs. What we're going to do is we're going to take whatever the highest demand is, and that's how fast we're going to run the fan. So our upper left here, we have a screen, and this is from the EMC software. This is the dashboard. It's probably the easiest way to look to see what the inputs are doing when we're adjusting them. So the lower section here is stimulus 1 through 4. And stimulus 1 and 2 are just potentiometers that are on the demo box that I can adjust with knobs and run the voltage up and down. So these could easily be thermistors that are in heat exchangers, and you're just looking at the temperature levels. Stimulus 3 is simulating engine temperature from the J1939 CAN bus. And stimulus 4 is simulating the intercooler or charge air that's coming from the J1930 CAN bus as well. Over to the right, we have the demand. So we'll be able to look at the demand as I turn the temperature up and the voltage is up. We can see what demand each input is producing, and then we can actually see the fan reacting to that demand. Over here, we can see the fan RPM. And right above it, we can actually monitor the engine RPM. Above that is a very nice feature for the EMC controller. We can actually run the fan in manual mode, which is a great diagnostic tool. Over here to the right, we have the display that's on the demo box. And the upper left, we have the engine temperature that we can adjust. Below that, we have a gauge that will show us the voltage 1 and voltage 2 temperatures or voltages as we move them up and down. Over to the right, we have a gauge called intercooler or charge air, and that will be able to adjust as well. And then we have the engine RPM. So the engine RPM, the intercooler, and the engine temperature are all being converted to J1939 CAN bus signals and sent down to the EMC controller to control the speed. The center gauge will be able to read the fan RPM, which is being sent up J1939 from the EMC to the display as well. Below that, we have our fan. I just have a camera hooked up to show that we'll be able to show us that the fan is running and operating correctly. So let's get started. So what I'm going to do first is we'll go ahead and we'll look at the stimulus 1, and I'm going to increase the voltage. So as I increase the voltage, you can see the demand goes up. And right now I am at 14% demand. So if I go to voltage 2 and increase the demand, once it gets past 14, it's going to take over. So now we're at 20% demand. So the fan's going to ramp up to 20% to 1180 RPM. So let's say my engine temperature starts increasing, but my voltage levels are the same. I'm going to increase my engine. And once it passes 20, now we're at 28 or 28% demand. You can see that the fan RPM follows whatever the highest demand is. Now I'm going to just adjust the intercooler up. So it's at 61% now. So you can see the fan speeds up to 1,862 RPM. So I'll go ahead and back off the intercooler. So now we're running off of the stimulus 3, which is the engine cooling. And one interesting feature about the EMC controllers, you can also set the engine RPM as an interlock. So let's say you want to make sure that the fans turn off when the engine's not running. Well, right now I have the engine RPM interlock set at 300 RPM. So once it drops below 300 RPM, it'll actually turn off the fans. So I'm going to adjust the RPM below 300. And again, it's just an interlock, but a very nice feature. So let's ramp it back up. So once the engine RPM comes up, it'll ramp back up to 28% demand. And we'll go ahead and we'll just back everything off. So now we just have stimulus 2 will turn down. And now it's running on stimulus 1. We'll turn stimulus 1 down. And now we're back to turning the fan off. So one other nice feature about the EMC controller, it has this manual on-off control. So I could turn that manual on-off control, and now I'm not even looking at the different stimulus inputs. But I can take the slide bar and I can just move it to how fast I want that fan to go, and it will follow this, the demand. This is a great troubleshooting option. You don't have to connect all the inputs up to see that the fans are wired correctly and that the fans are operating correctly. So next, I'd like to show you just what the current draw is for these fans at different speeds, because it's a nonlinear function. So as soon as you start dropping off the demand, the current draw of these fans drops off dramatically as well. So let me go ahead and adjust that. Okay, so now we're looking at the voltage level and the current draw. And so what I'm going to do is I'm going to go ahead and ramp this fan all the way up to 2,500 RPM. And let's take a look at the current draw. So as you can see, we're over 18 amps right now. And you can see my voltage dipping a little bit on my battery, but we're still at 18 amps. So now let's back it off to about half the RPM. So let's back it down to about 1250 RPM. So you can see that about half the RPM, we're clear down to 3 amps. So we went from over 18 amps to 3 amps just by cutting the fan RPM in half. So definitely something to note when you're designing these fans into your system.
Thank you for joining us today. And I also want to remind everyone that Hydraulic Controls Incorporated is a worldwide distributor for SPAL fans. So no matter what your location, feel free to reach out to any of our branches or our engineering team directly for your cooling requirements. Thank you.